is we have the b term multiplied by a natural logarithm. So we're going to reverse it. We're going to bring this particular coefficient 1 over h to be the exponent associated with this. So therefore, we have f prime of x is equal to the limit of the natural logarithm of 1 plus h over x raised to the power of 1 over h as h tends to 0. Okay. Now, what we're really going to try to do is we're really going to try to get from here a very important, let's say, identity. Okay, so we might recall also something really important is that the number e, the exponential number, okay, is equal to the limit, okay, of 1 plus 1 over n raised to the power of n as n tends to infinity. Okay, so this is an important identity that we have. We know that from definition. That's the definition of the exponential number. So what we're going to do is we're going to try to make this thing here look something like this thing here, and also introduce, that should be an n there, not a h, introduce, let's say this particular, introduce this particular constraint in relation to the term tending to infinity. So what we're going to do, we're going to consider the substitution. Let's say the substitution, consider the substitution. The substitution we're going to consider, so I'm just going to pull this out of the sky, okay? But the substitution we're going to consider is, let's say, h over x. So we're going to substitute h over x. We want h over x to be 1 over n, isn't that right? So h over x, I'm not really pulling out of the sky. I want h over x to be 1 over n. So let's do that substitution. So h over x equals 1 over n, okay? That's important for us. Okay, so let's have a look at this. So then we can substitute in here h over x or 1 over n, and also from here we actually have an important fact now. Also from here is that if h over x is equal to 1 over n, well then we must have that n over x must be equal to 1 over h, if that makes sense. Okay? That's important. Excuse me. That's important for us now. Okay, so now what we can actually do is we can actually make this particular substitution in here. But what happens to h, if that makes sense? What's really happening to h? Well, if you think about it in this situation here, okay, so what's h equal to? H is effectively equal to x over n. Okay, now h is meant to tend to 0. So how can we make h tend to 0 with this particular quotient here, with this particular fraction? Well, if n tends to infinity, which is exactly what we need, you can see that this particular fraction, as n gets bigger and bigger and bigger, this particular fraction is going to get smaller and smaller and smaller, so it's effectively going to tend to 0. So that's important for us. So now what we can actually do is we can change the limit, okay, to be the limit as n tends to infinity under this particular substitution. I'm just moving this across here now. So what we end up with is something really nice. Okay? It's probably all coming. Hopefully, it's all coming into shape now for us. Okay, so don't forget we have. Therefore, we have the f prime of x is equal to the limit of the ln of 1 plus h over x raised to the 1 over h as h tends to infinity. But we're substituting in for h over x, we're substituting in 1 over n. So this now becomes, therefore, we have f prime of x must be equal to the limit of the natural logarithm, okay, of 1 plus h over x becomes 1 over n, so it's 1 over n, raised to the power of, well, 1 over h is effectively n to the power. 1 over h is, from that substitution, 1 over h, the exponent here is n over x. So this becomes n over x. As instead of h tending to infinity, because we have, let's say, we have a change of terms here. So instead of h tending to infinity, what we have to keep the same, let's say, the same characteristics, we have now that n tends to infinity. Okay. Now let's just mess around with this here, because this is a logarithm. Yeah. So if we remember with logarithms and if we remember with exponents,